All right, so I want to start this angular momentum lecture off with a blank sheet of paper here, and then we'll move into the note guide. So you might want an extra sheet of paper as well, or two, or three, however many you think you need. But I would just try and have some on hand. Okay, so I'm going to start by dividing this page in half. And then to just do a quick review here, acceleration is equal to F over m, according to Newton's second law. And we also know acceleration is delta v over delta t. We can set these two equal to each other. And I think we did this a while back since they're both equal to a. And we can then cross multiply. And we get the impulse momentum theorem. And we also said, though, that F delta t is also J, right? Yeah, I just want to mention that real quick. That F delta t right here is J, which we referred to as impulse. Okay. Now, what we should be able to see from that as well is that we can state it a different way, right? We could say something like F delta t. And if we look at the other side, we see that this is final momentum minus initial momentum. So this is really delta p, right? Or change in momentum on the other side, which I can also write this way. All right, cool. And if there's no external forces, then we can say that, let me rewrite this really quick. Whoops. I'm going to rewrite it. Pi equals Pf. So momentum is conserved. Once again, that's when there's no external forces. All right, so in this lecture, we're talking about angular momentum. So we're going to need a variable to describe angular momentum. And we're also going to use the same trick that we just used right here to look at angular momentum, right? So by that, I mean we're going to use the same logic, right? So we have, instead of Newton's second law, A equals F over m, we'll have the angular equivalent, which is alpha equals torque over moment of inertia. And we also know that alpha equals delta omega over delta t. We can then set these two equal to each other, just like we did before, since they're both equal to alpha. We can cross multiply, just like we did over here. I know I didn't draw that in, but draw it in right now. And we can say torque times delta t is equal to I times delta omega. And here we can expand this out a little bit, just like we did over on the other side. I'm just kind of, following that as my my guide here. I have I omega F times I omega I. And here, I want to point this out. This is angular impulse. And we don't have a variable All right, and so yeah, I'm sorry to say there's no variable for angular impulse. Yeah, it's sad. All right, let's go ahead and keep moving. So we can go ahead then and write this we do have a variable for angular momentum. So we'll get to see that right now. Angular momentum, P equals mv for, let me write this down so that way you can see, you can just add it in there if you like. Over here we said P equals mv, right? This is kind of what we did. And over here we're going to say L equals I omega. And L is our variable for angular momentum. So I can, if you like, I can write that. Okay. And here we obviously have linear momentum. All right, so let's go ahead and come over here and write then torque times delta t, or angular impulse, is equal to the change in angular momentum, which is capital L. And it's delta, so change is the delta, but angular momentum is capital L. Okay, so I'm going to expand that out. And sometimes I like to use the script L, like cursive L instead, and that's fine too. LF minus LI, and now instead of saying F net equals 0, and if we can say if torque net equals 0. So if there's no external torques, right? And that's, and maybe I should say that instead, right? Because I think by saying net, it's kind of the wrong idea, right? It should be, and if force external equals 0, and if torque external, right, when there's no external forces, because there can be, forces internal, and that's fine. That doesn't change momentum, right? And then internal torques don't change angular momentum, is what we're going to see here, or what we're trying to say. So if there's no external torques, right, then we can say, I'll rewrite this one more time. We can go ahead and set external torques to 0. So we get a 0 over here, because 0 times delta t is 0. We can see that angular momentum is conserved. All right. And so this is very, very symmetrical to what we learned about linear momentum. And I just wanted to point this out. And we also found a new variable for angular momentum, which is capital L. So if with no external torques, or no external forces, Pi equals Pf, momentum is conserved. With no external torques, Li equals Lf, and angular momentum is conserved, is the big idea there. All right, so let's go ahead and move into this note guide now. I'm going to pause it for 1 second. All right, so getting into the note guide itself, we're going to skip over part of this just because we kind of already talked about it before. So we won't have to worry about this right here. Unless you want to read it, you can. Otherwise, we already discussed it. And down here, we actually have angular momentum equal to, just like we had linear momentum, P equals mv. We now know angular momentum is I times omega. And the reason I'm bringing this up right now is because I want to talk about the units then on this, right? The units on I were, I always remember that because I think of a point mass. The moment of inertia for a point mass is mr squared. And if that's the case, then we know our units on I are going to be kg times meters squared for the r squared. And we then know omega, right? Omega is like velocity in meters per second, but it's in radians per second. So radians are kind of a shadow unit. So if we put these two together, we get kilograms times meters squared over seconds. And this is our SI unit for angular momentum. All right. Anyways, I just wanted to point that out. Moving on in the note guide. Once again, we're going to kind of skip this next part because we already kind of talked about it, that the law of conservation of momentum exists when there's no external torque. The law of conservation of angular momentum exists when, the law of conservation of momentum exists when there's no external force. The law of conservation of angular momentum exists when there's no external torque. So this is true or when there's no external torque, or when torque external equals 0, right? And yeah, so either way, the net external torque is 0, or there just is no external torque. One of the two. All right, and then we get Li equals Lf. Something that's interesting and maybe worth pointing out here is that the initial and final moment of inertia may not be the same. We never saw this with Pi equals Pf, meaning the masses were always identical, right? That an object wouldn't gain or lose mass. But a moment of inertia can change. You can think about this if you're spinning in a circle and you pull your arms in, right, like a figure skater, and then therefore the moment of inertia of you spinning is different. It's smaller, right, when you bring your arms in, and so that's what we're going to see happen in some of these examples down below. So let's go ahead and look at them. This first one, I know I didn't leave myself a lot of room, so we'll try. We'll see how it goes. I think I got some extra room below because I knew I wasn't going to have enough. But yeah, make sure you have that extra sheet of paper handy. All right, so it starts off with a drawing of about Joey and on a merry-go-round. So I always like to do, hold on one second, let me get rid of that. All right, I always like to start with before and after drawings. I'm just gonna go ahead and make all mine down here because I just want a little more room just in case. All right, oh, that's sweet. All right, no, I can't get those blue dots off there. All right, there we go. So we have a merry-go-round, something like this, right? And it's going to be spinning about a center point and axis of rotation right in the middle. And to start with, Joey is going to stand at the center. All right, so this is where Joey's going to stand. And we know that the mass of Joey is equal to, they tell us, 36 kilograms. And they tell us that the radius of this merry-go-round is 2 meters. And they also tell us that the mass of the merry-go-round, I'll just call this mm, I got mj up there, is equal to 200 kilograms. All right. So, okay. So then they say, while it's rotating, Joey walks out to the edge of the merry-go-round. All right. So this is an instance where the moment of inertia is going to be different for Joey before and after. Because when he's at the center like he is now, Joey's moment of inertia is going to be 0. And because he doesn't have a radius, a distance from the moment, from the pivot, right? So I'm saying that ij initial is going to equal 0 for Joey. And for the merry-go-round itself, I think there's a hint up here. It says the merry-go-round's moment of inertia is 1/2 mr squared. I think that's for a solid cylinder or a disc. So anyways, we know that that's the case. So I of the merry-go-round is equal to 1/2 mm, right, times r squared. Okay. So in the after drawing, the merry-go-round isn't going to change, right? It's just going to kind of do its thing. Well, in terms of its moment of inertia. But Joey is now going to go live on the edge, stand on the edge. All right, out here. Okay. So, all right. Anyways, so when he does this, he now has a distance from the axis of rotation, right? Which we know is equal to r, which is 2 meters. This means that Joey's moment of inertia, this is really all that's going to change, right? I Joey final is going to equal, well, he's a point mass, so it's going to equal mass Joey times r squared. Moment of inertia for the merry-go-round is still going to be the same. Mass of the merry-go-round is still going to be the same. And what we want to know is how this changes the situation, right? I think they tell us to calculate the final angular velocity of the merry-go-round, the final frequency and period of the merry-go-round. And so we want to know how this is going to work. And they start off by telling us one piece of information initially. They say that it's rotating. Let me see if I can highlight this. It's rotating once every 2.5 seconds. All right, and this is when they tell us that it's making one revolution every 2.5 seconds or one cycle every 2.5 seconds, they're giving us a frequency right here. So I want to point that out. We should remember, right, and I'll write that down, F equals one cycle or one revolution, I could have said. I'm going to say revolution. Every 2.5 seconds. Okay. All right, so there we are. So what we need, right, is we want to use our angular conservation formula. But I just want to highlight again what they're asking us. So they want us to find rotational period of the merry-go-round when Joey gets to the edge. Okay, so I think if we find the rotational, or if we do conservation of angular momentum, we can find the final angular velocity, get the final angular frequency, and then turn that into the period, right? Because we know, or should remember, that that frequency equals 1 over the period, or a period is equal to 1 over the frequency. Another formula we have to use here is we know that angular velocity is equal to whatever one surround is, 2 pi radians, right, times the frequency. So we're actually going to take advantage of that formula to know what the initial angular velocity is, right? That's what we're going to want to find out. So let's go ahead and use that down here. So 2 pi radians. And this is the initial frequency. Final frequency is probably going to be different because its angular velocity is going to be different, as we're going to see. So we'll multiply this by the initial frequency. And so we're getting what here? Let's see. All right. I don't know if I already have this. I think I do. This ends up being about 2.51 radians per second. You might say, well, what happened to the revolutions on top? Well, we have to remember that when we use this formula, right, it's really like it's saying that this is 2 pi radians per 1 revolution, right? And then the revolutions cancel away, and that's why we get what we get. All right. All right, so there's our initial angular velocity. Now, why did I go ahead and get that right? It's probably a good question, because we know that angular momentum is conserved. There is no external torque, and therefore that's true. That Li is equal to Lf, and we can now go ahead and write out what we have for our problem, right? Which is that the angular momentum of Joey plus the angular momentum of the merry-go-round initial is equal to the angular momentum of Joey plus the angular momentum of the merry-go-round final. And so so what I'm saying there then, if we remember that L is equal to I times omega, we can go ahead and write this initial for Joey and initial for the merry-go-round. So I'm saying that we will have I Joey initial times omega I. Now we have to remember, like, both Joey and the merry-go-round, because Joey's on the merry-go-round, his angular momentum, or no, angular velocity initial is going to be the same as the merry-go-round. And that's going to be true on the other side too. So I'll point that out here in a second. So I'm not going to differentiate omega I because they're the same for Joey and the merry-go-round, because Joey's on the merry-go-round. Okay, all right. We have plus I m initial. I guess I don't have to write initial here either, because the merry-go-round's moment of inertia isn't going to change, times omega I equals I Joey final times omega F plus I merry-go-round times omega F. Okay, so something like that. And now we can go ahead and add in those values. We said up here that Joey's initial moment of inertia is going to be 0. So this entire term here is going to cancel away. And we said that Im is equal to 1/2 mm times r squared times omega I, which we know omega I is 2.51 2.51 radians per second. We can then set that equal to I Joey final, which he's a point mass. So we're going to have the mass of Joey times r squared times omega final, which we don't know. That's actually what we want to solve for, times Im, which is the, once again, the 1/2 mm r squared times omega f. Now, something you might notice here is that both of the terms on the right here are being multiplied by omega f. So you could have wrote that differently, and I could have did that for the front as well, or the left side. So I'm gonna show you what I mean here real quick. And so I'm saying that I don't know if I have. Do I have a mass of the merry-go-round? I do. Okay, it's 200. I forgot to write kilograms, dang. All right, I'll just jot it in right there. So what I'm trying to say here is that you could have wrote, let me see if I can, I'm going to do it this way. I'm going to use a bracket. So we have mass of Joey, which is 36, I believe, times the, sorry if this is getting hard to read, times the radius, which is 2 meters squared, times omega f, which I'm going to hold off on writing because I'm going to show you, I'm just going to move it to the outside, right? So I have, whoops, let me erase this. I'm kind of running low on room, so I'm going to try and squeeze all this in here. Times r squared, which is that 2 meters. And I could have just moved omega f outside of the bracket. So I could have just had it out there, right? All right, so anyways, let's do a little math here and make this easier to look at. On this left side, I think we're going to end up getting over here for about 400. And multiplying that by 2.51. On the right side, we're going to end up getting, let's see here, keep this bracket, 144 plus, what would that be? I forgot my square. I think I did, yeah, I just noticed that. All right, so yeah, you can't forget to square a radius there. So anyways, we're going to get half of 200, which is 100 times 4, so 400. Okay, so a little more math here. I don't have this, but I do have the final answer, so I'm just going to go ahead and go with it. I would suggest you do that math out yourself, and I guess I can make it a little simpler to look at. This is what, 544? All right, divide both sides by 544, crunch the 400 times 2.51, and we get omega f is equal to 1.85 radians per second. Now we remember that the problem, I think, asked us for the final frequency and final period of the merry-go-round. So let's go ahead and solve that. So we can say omega f then is equal to whatever once around the circle is times the frequency. This is the final frequency, which we want to know, because if we know that, then we can say that the period final, right, is equal to 1 over the frequency final. All right, so let's go ahead and solve this equation first. So we're saying the frequency final is equal to omega f over 2 pi radians. So we can say frequency final, right, that's kind of what I'm saying, is equal to 1.85 radians per second divided by 2 pi radians. All right, so those radians are going to cancel away. And we're going to be left with per seconds, which is what frequency is. It's in seconds to minus 1, also known as cycles per second, right? Cycle is one of those shadow units, once again, that we don't really worry about. This is a 5 right here. Okay. And if we do the math there, I think we get about 0.294 cycles per second, or revolutions per second, or if you just want to write per second and don't even write cycle up above, that's fine. Or you could say 0.294 hertz. I'm going to go ahead and write the 1 underneath. Okay, so, but once again, we wanted the final period. So we're almost done here. All right, so we're going to say then the final period is equal to 1 over 0.294. And this is going to, we have a fraction inside of our fraction, so we have to multiply by the reciprocal. It's going to put seconds on top and cycles on bottom, which is what period is. It's the seconds per cycle. All right, so we have TF then is equal to, and I don't know if I have this crunched. I'm going to get my calculator. Are you serious? Give me 1 second. Oh, I got my phone right here. I just like using my calculator. Guess I could just use my computer. Oh, let's see. Just trying to avoid this. Should always have my calculator out. All right, so we have 1 divided by 0.294. I'm getting about 3.40 seconds. Technically, this is seconds per 1 cycle, or 1 revolution. Okay, so there's our final answer right there. And we are done. All right, let's try the next problem. And I may add another sheet of paper in right here, because I like to write large. And let me see. Okay, I think that'll work. All right, so the next example, 9.11, it says an ice skater spins around on the tips of his blades while holding a 5 kilogram weight in each hand. And he begins with his arms straight out from his body and his hands 140 centimeters apart. Okay, so in this case, I'm gonna try and draw this up here. So I have a person. Once again, whoops, dang. once again, this is the before drawing. And we have a person holding the weight straight out. And spinning. And then in the after drawing, the person's going to bring those weights in. Let's see. How am I going to draw this? Like that, right? And this distance right here is 50 centimeters, so 0.5 meters. And this distance right here is 140 centimeters, or 1.4 meters. But we don't really want those distances, right? We want to know the distance from the weight to the center of rotation, the axis of rotation, which is straight through the person's body, right? And because they're spinning around. And so what I'm saying is then this distance is what we care about. This is r. And this is going to equal to half that. So this is my initial r, right? I guess I could call that r initial. And r final is going to be this, which is equal to what's 0.25. All right, and we were told to ignore the mass of the person because their mass is going to be spinning away from the axis of rotation. I'm sure some of it will be spinning right at the axis, but a lot of it will be, around it, and so we can ignore that and just focus on the mass of the weights, which is 5 kilograms. So I can just write m equals 5 kilograms, and that's true of both masses, right? This is also m, and the mass doesn't change. But the moment of inertia is going to change, just like we see before. I think they tell us that the person is initially spinning with a frequency of 2 revolutions per second. Which we know that's pretty much giving us angular velocities, so we can convert that just like we did before, right? Where we can say, because this is initial, we can say omega I is equal to whatever once around the circle is, which for angular velocity is going to be 2 pi radians. If it was once around the circle in linear velocity, then we would say 2 pi times the radius, 2 pi r, right? That's the distance around a circle in circumference. All right, anyways, 2 pi radians times frequency initial, and we can go ahead and solve for that. Let me see if I already have this solved for. I don't know. So we have, did I do this already? I don't think I did. Yeah, maybe I did. I think it's 12.57. So we're saying that this is true. We're going to multiply this by 2 revolutions per 1 second. And we're going to end up getting 12.57 radians per second. Okay. And so the question is, what is the final angular velocity? And then they want us to know how fast is he spinning in revolutions per second. So we're looking for that final frequency, right? Okay, so we did our drawings. I think we're good there. Calculation, just like before, we're going to say Li is equal to Lf. And I'm going to be able to do what we did before, right? Pretty much the same way. And so we can say then for initial, since both masses have the same angular velocity initial and the same angular velocity final, and this is what we want to know is angular, geez, I'm having a hard time writing that. Let me just start over there. We want to know what is the final angular velocity, right? And we'll find that first, and then get frequency final, which we also want to know. So we'll use the conservation of angular momentum, and I'm saying we can have, since both masses have the same initial angular velocity, we'll have mr squared I'll write it like that, plus mr squared times omega I is equal to, once again, mr final squared. Times omega f. All right, so we have something like this. We said the mass, was it 5 kilograms? Yeah, that's pretty hefty weights there. All right, so I think this initial radius was 70, right? Or 0.70 meters, 70 centimeters. So we're going to go ahead and square that. I'm not sure why. Oh, I see what I did. This should probably be a bracket. We're going to multiply that all by initial angular velocity, which was that 12.57. Running a little bit out of room here. This is just going to look a little rough. I'm going to use brackets again. This was 0.25, I believe. And then this whole mess over here is multiplied by omega f, right? So I just don't have room there. I'll just draw an arrow. And there's supposed to be an omega f there. Okay. So, all right, let's make this look a little nicer, right? Okay, I have some of this already done. So, turns out this is 4.90. Turns out that we'll just multiply this by 12.57. And over here, we have that this is 0.625 kg meters squared times omega f. Just try and keep that separate from what's above it. Okay, so we have something like that. All right, so now we just multiply the left side, divide by 0.625 on both sides, and we should be good. We should get radians per second as our final units, and it's going to be omega f is going to equal 98.55. All right, so what we're seeing then is that this is a lot faster, right? Because I think it started with initial angular velocity of 12.57 radians per second. this really picked up the pace quite a bit. Okay, so let's go ahead and finish the problem. We want to know how fast he's spinning in revolutions per second, which is the same as frequency. So we're going to get the final frequency then. I think last time we said, just a second ago, we said omega f is equal to 2 pi radians times frequency. And so we can say frequency is equal to omega f over 2 pi radians. So we can go ahead and say then 98.55 radians per second divided by 2 pi radians, which is going to equal 7.84 revolutions per second. So that's spinning pretty fast, right? Almost 8 times a second. Yeah, that's cruising. All right. Is that realistic? I don't know. It's a good question. Dang, I don't know if I like that. Oh no. All right. I need a yellow highlighter. Oh, dang. That's so difficult. All right. So there we go. There's our final answer there. And this is the final frequency or the final angular velocity in revolutions per second. So you see that the two are kind of the same, right? That frequency and angular velocity are kind of interchangeable. All right, good. So we have one more thing left. It looks like a stop to think question. And so let's go ahead and take a look at that. It doesn't have a drawing here, so we're going to have to add one in. And the book does this problem as well, but I didn't know if I really liked their explanation or their drawing, so I do it a little bit different, but feel free to reference the book's question. It says the left figure shows two boys of equal mass standing halfway to the edge on a turntable, so a merry-go-round, that is freely rotating at angular speed omega I. Then they walk to the position shown in the figure, and the final angular speed is different, or is what compared to the initial angular speed, right? So once again, this is one that doesn't require a ton of math, and so I think it's a good example of maybe of what they would ask on the AP test. So, but it's still a tricky problem, so let me go ahead and draw this merry-go-round. And I'll put an axis of rotation right in the middle. It says that the two individuals are standing like so. Now I'm going to give this a numerical number, or I'm going to call it R. Now I'm just arbitrarily calling this distance R. R is usually the full length of the radius, right? But I don't know. I could have called it. No, actually, do I when I saw this, I usually call it R. I think I do. I think I've done it that way in the past where I call it R and 2R. I think this time I'm going to say that R is equal to 1 meter. Just for this drawing, right? Because on the next drawing, R is going to equal 2 meters. So they're halfway. Whoops. So they're standing halfway out from the axis of rotation. Then they're going to move to this position. Still the same merry-go-round. Oh, jeez. This is what I get for trying to utilize technology. Oh, my Lord. All right. So one of them is going to stand right in the center. So his or her moment of inertia isn't going to matter. And the other one's going to stand, because their R is going to be 0, right here. And the R of this one is going to equal 2 meters. Okay. And so I'll just write that down, that this one has an R of 0 meters. That's too bad. All right. So anyways, good. So we can look at this a couple ways. And so in my notes here, I actually worked it out 2 ways. I don't think the problem tells us anything else. Oh, it says they have equal mass. So each boy or girl or each kid has a mass of m, we'll say, for their mass. And all right, so the first way I want to work it out is ignoring the moment of inertia of the merry-go-round, just like we did the problem before, right? And so what I have then is I have Li is equal to Lf. And then we can say we have what here? We have mr squared. And I don't think in times omega I for one of the boys or girls. Is it boy? What the heck? 2 boys. Okay. Jeez Louise. All right. So then we have, and I'm writing it the other way this time, right? I could have wrote mr squared plus mr squared times omega I, and I didn't do that. All right. And then on the other side, we have mr squared times, this is where it's okay, where it starts to get different, right? So let me just write it this way, and then I'll go through and clean this up. Oops, dang. All right, so we have something like that. But we just said over here that this R is, yeah, we'll just go ahead and put some values in. So we have m times 1 meter squared times omega I plus m times 1 meter squared times omega I is equal to m times 0 meters times squared times omega f. And you can see that that whole term is going to equal 0 plus m times 2 meters squared times omega f. And so we're going to end up getting, and this is where the meters start to look a little bit like the m values, right? So I'm going to rewrite this. I have 1 meter squared m omega I plus 1 meter squared m omega I. So I should get 2 meters squared, right? Times m omega I. Yeah, okay. And then on this side, we can go ahead and get rid of this. And we're left with this. Don't confuse the m's. I'm trying to write it in a way that it makes sense. All right, and then we can go ahead and say, well, we got an m on both sides, right? That's the mass, and we can cancel that away. What else can we get rid of here? We can probably get rid of a lot. Let's rewrite this. So I'm gonna go ahead. I want to know how omega f compares to omega I. So let's get rid of the 4m squared on this side. So I'm saying we'll just divide both sides by 4m squared, right? I can do that up here if you like. And I'll be left with 2m squared over 4m squared, or 4 meters, I gotta be careful, 2 meters squared over 4 meters squared times omega I. So what's 2 meters squared divided by 4 meters squared? Just 1/2, right? The meters squared are both going to go away, and 2 divided by 4 is a half. So we're saying that 1/2 times omega I is equal to omega F. Boom. So the correct answer then is that the final angular velocity is going to be half the initial angular velocity. So we're saying correct answer would be B, right? Less than. Okay. It's going to actually be half of what it was initially. Now, another way to look at that is if you included the disk as well, right? You could have said, well, then omega I, or not omega I, sorry, I, moment of inertia initial is equal to I disk, which we don't know what it is, but probably 1/2 mr squared. But if I guess we could find that, right? Because we did define R as being 2 meters. And but we don't know the mass of the disk, so whatever. I'm just gonna leave it I disk, and all right, time or plus the mass. Whoops. Plus the mass of one of the boys times 1 meter, which I'll write it as. Should I leave it as 1? Should I? Let me think about this. Just all the M's there just get confusing. I don't know if I want to write meters squared or not. I'm gonna go ahead and write it. Just hopefully, I think it'll make sense. All right, and then we can say that totals up to what there? I disk. And then this is going to be equal to M times 1 meter or 1 meter squared M plus 1 meter squared M. So it's going to equal to 2 meters squared times M. All right, so we can see that that's true for the moment of inertia initial. And for the moment of inertia final, we can say the same thing, I disk, of course, plus M times 0 meters squared, which is just going to go to 0, plus M times 2 meters squared, and we're left with I final is equal to I disk plus 4 meters squared times M. All right, so we can clearly see which is larger here, right? We're comparing the moment of inertia initial and the moment of inertia final, and the larger one is going to be IF, right? So this is going to be larger. This is going to be smaller. And so what I'm trying to say is if IF is larger than II, then we can say that omega, in order for angular momentum to be conserved, right, where Li equals Lf, and this is saying II times omega I is equal to IF times omega F, that if IF is larger, right, let me see, if IF right here gets larger, then omega F would have to be smaller, right, is what I'm saying. So So what I'm saying, once again, then, is you can make your moment of inertia larger. But because there's no external torque, and this equal sign is here, that if these two sides have to stay equal, that omega F has to get smaller to balance that out. Because maybe Li is 100. I'm just making up a number, and LF then also has to equal 100. And so in order for that to be true, right, in order for this equation or this equality to hold up, this has to be true, right? That if IF is greater, then omega F has to get smaller. All right, so the merry-go-round slows down. All right. Good. Hopefully that's making some sense. So once again, answer B is correct. And if you have any questions, let me know. And have a good day.